My name is Tohid, and JP has given a nice introduction, so I don't need to waste time on that. So I'm jumping on to today's topic. So at first, I would like to thank you, the MRI Together organizer team, to invite me as a speaker of this session. And as you know, I'm from Monash Biomedical Imaging, Australia, and today I'll share our experience developing the first MICCAI challenge for ultra-low field MRI image enhancement, and focus on how data sharing, harmonizations, and some of the ethical consideration that enables reliable AI for emerging MRI technologies, especially for the ultra-low field, like the 64 millitesla MRI. So today's overview of this talk, it would be, first I would explain the motivation behind the ultra-low field MRI and why data sharing is particularly important aspect in this space. Then I'll walk through how we built and harmonize the paired 64 millitesla and 3 Tesla datasets, followed by detailed look at how the ultra-low field image enhancement challenge design. And also at the end, I will highlight some key ethical consideration, technical and operational lesson we have learned by doing this challenge, and finally outline the future direction of the ultra-low field MRI data sharing aspect. So first, why data sharing matters. So data is like ultra-low field MRI system, like hyperfine soup brings MRI close to the patient. For example, the main feature of this MRI is portability, so it can move from one room to another location. And it's low cost and ideal for emergency department, rural regions, and resource-limited hospitals. But the biggest barrier is the image quality, the low SNR, thicker slice thickness, and different contrast behaviors, making the interpretation of the current image produced by those scanner is challenging. This makes AI enhancement as a one aspect of the compelling path, but AI only works well when high quality and standardized data sets are available due to like the training and validation purpose. So when we started this project, there are no publicly available paired 64 millitesla and 3 Tesla datasets. So this meant the researcher could not compare the methods fairly, could not reproduce the results, and struggling to evaluate the generalization across different settings. So data sharing is therefore not optional. It is the fundamental to building the trustworthy AI system for low field MRI and ensuring clinical impact beyond a single research center environment. So our data set was collected primarily from Monash Biomedical Imaging using paired acquisition, meaning the same participants received both 64 millitesla and 3 Tesla scans in the same sessions, one after another. There is no strict rules which one would go first and which one will be the second. We covered a wide range of ages, used standardized recruitment. Ethical approval was also obtained from Monash University. And because paired data increased the re-identification risk, so we used an identical facial removal across the both methods. So this ensures strictly privacy protection from the beginning. So now it's highlighting how different acquisition physics and resulting images are. the 3 Tesla system provides high resolution, as we know, like mostly it's 1 millimeter isotopic in our acquisition setting for T1 and T2. And the 64 millitesla produce the lower resolution images with thicker slice thickness. That's also have like, because the gradient strength is lower, so inherently it's produced the noisy type of image and have low signal to noise ratio. This inherent difference means enhancement model must learn both resolution recovery and contrast mapping. So it's kind of like not one task matter thing. And it's not really a like super resolution consideration. So it's kind of recovering the contrast and also the resolution as well. This paired structure motivates the challenge design. So like when we have the benchmarking, for example, what we're trying to achieve is on our hand, so we can like validate any model or aspect of this. And to ensure consistency across all subjects, we built a harmonization pipeline with manual quality control of every scan. So whenever a subject scans, so we quickly go through almost slice by slice for every subject. And there is also a standard procedure placed in molecular biomedical imaging. So if there is any incidental findings occurred, so there is some standard operating procedure to inform the participants or the participants GP or someone responsible. First, we converted all the DICOM images to the Nifty. Then we applied the bias field correction, and because this is the nature of the dataset creation is paired, so we did registered the 64 millitesla image to the 3D space. All scan was resampled to 1 millimeter isotopic resolution to make comparison feasible. For example, any downstreaming task like segmentations or volumetric measurement that makes easier. Finally, an identical face removal mask was applied to prevent re-identification across the modalities. In our particular case, we actually didn't use the automated face de-identification approach. Rather than we just crop a part below from the nose to ensure any facial re-identification feature has been removed. And since the data is co-registered together, so one modalities cropping is applied to other modalities. This standardization was essential for downstreaming AI training and evaluation, and because another reason was not using any existing de-identification model, because we identified that this model is actually, because this model is actually haven't seen any ultra low field type of image, so it is produced some unwanted like masking. So about the dataset, so our dataset contains T1, T2 flare images for each participants. Actually, we collected more data for our different purpose, but because I'm going to share the information about related to the ultra low field enhancement challenge. So in this challenge, we just only consider the T1, T2 and flare images. So we structured this data into clear train, validation, and test split to support the challenge. And the headout test set is never released, ensuring the fairness process during the evaluation. We also created a consistent folder that naming scheme which significant reduce the user error and improve the reproducibility of the participant pipeline. So there are some measurement we had to keep. For example, like with specific de-identified data is actually used for training, test, and validation. So we had to track a separate record for that to make sure we're doing it fairly, not mixing up with the training, test, and validation data. So why create the MICCAI challenge? So one of the major considerations was choosing the correct data license is one of the aspect. The licensing and data governance, the part. So one of the major consideration was choosing the correct license because the data set contains paired scan, which are more likely to identifiable because we have like 3 Tesla and the low field as well. So we choose to most commonly use CC, BY, NC, ND license. This means the data cannot be redistributed, commercialized, or modified without the permission. Participants must cite our foundational papers and cannot publish the challenge specific findings before the joint paper is accepted. This framework protects participants while enabling the meaningful research. So before we give the access to our data set to participants who wanted to participants, we have a DUA assigned by the participants that's having those terms and conditions, the uses of the data sets. That was part of the data sharing policy. And why MICCAI challenge? So we launched the ultra-low field image enhancement challenge to establish the first benchmark of ultra-low field MRI enhancement. A challenge creates standardized evaluation environment, allows fair comparison across methods, and brings other global working on a community in one place. And particularly MICCAI challenge is actually designed to have host this kind of initiatives, to have a benchmark, to bring other experts together to find out a solution that one team may not be possible to find, and explore a different multi-directional approach to find the solutions. And another, as the nature of the MICCAI and its reputation is also increased the visibility of the scientific aspect of the ultra-low field MRI research. So that's a few things encourage us to go for the MICCAI challenge. Some of the challenges is to make the decision of initial decision of how we're going to share the data. So because we are having the the original DICOM image, and are we going to share the DICOM image after re-identification, or we should do some processing and share it to others in a manner of avoiding unnecessary steps can be done by multiple participants, and then it could be lead to a generalization issue. So what we came up, we provide some of the pre-processing steps and the clear documentation, and then share the data, so it would be much more easier for other to directly use the data set and have much more balance or fair comparison with other participants. So the challenge data set includes 50 training cases, all are paired, 10 validation cases, and 15 held out test cases. We hosted everything on Synapse. It's a publicly accessible open source repository, and also it helps to organize the challenge, record or provide access to the participants. And also we publish the GitHub evaluation tools and script that used as part of the challenge, and all submission were Docker based at the end. So that means that Docker makes sure the reproducibility. So what we did at the end, we asked the participants to provide their Docker from their side, and along with the necessary script. And what we have done from our side is to provide that 15 test case data to the Docker and generate the output. So we enforce the inference constraints, a maximum of 40 gigabyte of GPU memories and 2 minutes of runtime per cases. We had to set those things because the data is 3D and there are a very strong motivation we are feeling. The user, the participant may have come up with the 3D diffusion, and because we have the limited capacity for validation and test, so we must set some specific rules that the participants follow. Otherwise, we would having more time to put on those validation and test, because a single user can provide multiple validation and testing Dockers. The evaluation metrics and ranking. So that's a tricky part, I would say. According to the MICCAI, one of the standard is to provide a clear instructions how we're going to use the metrics and ranking. So we designed the ranking scheme prioritizing anatomical fidelity, structural similarity index, or SSIM contributes 70% of the final score, because it best reflects the preservation of the meaningful brain structure. PSNR, MAE, and normalized mean square error is contribute 10% to ensuring we also capture the intensity-based and error-based aspect. And finally, if two teams achieve the same score, the inference speed serve as the tiebreaker. So any teams, if have the tie, then how we can differentiate both. So those models are inference time is faster, consider desired. Okay, so the evaluation pipeline, to minimize the submission failure, we implemented a sanity checks phase where each participant's Docker contents run on a small subset of the data. Teams can submit multiple times, but only the last successful submission is scored. And each submission must produce a full 3D output of the multi-contrast images. This ensures the consistency and fairness of the evaluation process, and it'd be much more easier for the organizers to have score them as early as possible, because we have multi-contrast data, and if some of the team produce slice by slice, so it would be a very computationally intensive task to compare and send the score to the participants. And when the number of participants increase, like for example hundreds or a few hundreds, then it could be like very challenging task. So what we have learned from the challenge, from the ethical standpoint, paired data set are more sensitive than standalone images. And since we are based on Australia, so there is a ethical additional ethical consideration was set by the ethics committee. Is like the data should not be transmitted over outside of Australia. So then we had to like back and forth communication to establish like what could we do for this to make it publicly accessible. So and then when we used the face mask and remove, like we're not sharing the DICOM, so all the identification information was removed, and then like we are been able to have this data set publicly available. In the harmonization aspect, because we practically use one center data, so and at this aspect we just had to go through with that multiple contrast to make sure they are aligned together and showing no additional artifacts. Those kind of things make it like I would say a bit easier for us to make it harmonize between multi-contrast and 3D and ultra-low field. Another thing is we had to put an embargo to protect the participants to not use the data set after the publication, after the challenge was concluded, because we wanted to have a summary paper that would be published by our team, like the organizer team. So after that, we would say the dataset is fully open for anyone for any type of research purpose. So the technical aspect is definitely the low SNR of the ultra low field image make it hard for us to finding any like artifacts, especially for the non-technical person like me. So I have no knowledge about the MRI, and my background is only computer science. So that was challenging. Most of our team members also similar. Another is the registration failure. So some of the images we scans we came across, they have a different orientation, and if there are more than certain degree of differences in the paired data set, so the co-registration may fail, and we had to exclude few paired scans due to the co-registration. And another reason, because none of the co-registration algorithm have been trained with ultra low field, so that's another limitation we are facing during the co-registration. Another very important thing is the Docker reproducibility. So there are many challenges. Individual participant team may come up with some Docker that may not work in our end. and we had to communicate with them back and forth. Even sometime had to have online session to understand what's going on and overcome those limitations. So that's also a lesson we have learned. The sanity check also another important thing we need to make sure. Otherwise, we may don't know what's the automation thing if we put in place are doing. So it's always better to have some small sanity checks to see the score and see the actual prediction and if that makes sense or not. So that's also another aspect of lesson we have learned. Some of the operational challenges are documentation matters. So as early as we can start putting those documentation in place is better. I know it's somehow we always miss those things. Like we thinking maybe after some certain level of time, maybe we can put those things together, but that's not really working. So documentation is must and very helpful. Clear instruction, also reducing participants' questions and errors. Providing a discussion forum is very beneficial for engagement with the participants. We also realized the importance of timeline buffers. So there should be a buffer session, buffer timeline put in place, especially when having Docker environment, and many team can come up with different type of libraries and other things that always makes things challenging for the organizer team and the participants team to work together and produce the results. So one of the most exciting outcome was the strong global interest in the ultra-low field MRI community. We saw a rapid adaptation of diffusion models among the participants and growing enthusiasm from the open hardware community. And those motivational things actually like a rewarding to us to have motivated for what we can do next, as we are almost like leading the Australian ultra-low field MRI research here. And another aspect is the cross-disciplinary partnership, like between engineers, physicists, and clinician. Also, very exciting thing. So, looking ahead, we plan to expand the data set of multiple Australian sites, which will greatly improve the generalizability. We are developing population normative brain template for 64 Tesla MRI, as well as exploring diffusion weighted acquisition at low field. Federated learning is another promising directions. Enabling cross-site collaboration without centralizing sensitive data is also another future directions. So at the end, I'd like to acknowledge the support provided by the National Imaging Facility, Monash Biomedical Imaging, our organizer team, advisory committee, and the MICCAI challenge organizer chair. Their contribution made this work possible. And thank you for your attention, and I'm happy to take any question and welcome the opportunity to collaborate in future in this direction of data sharing, and especially for the ultra-low field.